Okay, my name is Huitzimengari Campos Garcia. I'm a plant ecophysiologist from Mexico, and I am also a professor in two universities. One of them is Universidad de las Américas, Puebla, and today I'm going to talk about the exercises that we did with the Stella Q2 sensor in the classroom. So I'm gonna talk about the two examples that I took from my students. One of them is Mariana Alvarado, Malagon. And what she did was to relate the spectral signature, take it from the Stella Q2 sensor and use it to correlate it with the name species of several plants. So let's begin. The light, some physical characteristics from light, and we can see that the visible light is only from 400 nanometers to 700 nanometers, but there are also other bands that are happening right now in the light. So these bands could carry information about the surfaces that reflected that light. So that is one of the usefulness of measuring light or quantify light with sensors like Stella Q2, no? When we illuminate a surface, this surface then will absorb some light and reflect another one, creating a spectral signature that we can see here. So we have different species and its spectral signature that is very specific for each species. So it's very useful, or it will be very useful to do taxonomical studies. I mean, I don't know if you have tried to identify a plant species to the species level. It's very difficult. You need a lot of knowledge about taxonomy, plant botany, but with sensors like the Q2, we can do a faster measure and try to figure out which species it is. And this is what Mariana did. So we built the spectrometer Q2 sensor in the classroom, and then we go outside to take several measures in different plant species. Some of the results were these ones. We find different kind of spectral signatures. You can see here for Agave, Bauhinia, Yucca, and its picture or photograph. And here down we have Cupressus and asparagus. So also that the other important thing that we find is that we have bad data with a lot of noises in it. So we have to improve our measurements, and we want to spec these kind of measures that are here down. So the variation is smaller than these ones. Another importance is that we have to do the white card correction for each measure. But in this case, we have very little time. The semester was ending, so we used the raw data direct from the Stella Q2. For that reason, and another ones like this highly variation, we found a lot of noise in our data when we did the principal component analysis. Principal component analysis is a reductional information procedure. So we have 18 bands, and those information of the 18 bands, we reduce to 18 principal components. So with that reduction, we have 89% of all data variation. Then we plot the first two principal components that they explain 89% of the variation. So we can see that every ellipse for is the signature of each plant. Here we can see that because the highly variation in the data, they overlap one in another. So the discriminant function was not very well. Indeed, when we applied the classification method, in this case, we applied a multinomial logistic regression to predict the species. Because all highly variation data, we found only the accuracy of that model was only of the 14%. This means that 86% of the classification was wrong. But all this could be improved. Indeed, when we are going to see later that with another data set from another researchers that they did the white card correction, they improve a lot the classification and the discriminant function of the principal component analysis.
That's amazing. That's really,
yes. So, but I think that thinking in the work that my students did for a semester in the classroom, this example is great for they to work in his experimental skills, also computational skills and statistic skills. So it's great that they carry on an experimental procedure in his background. So it's great to did this kind of exercises in the classroom.
Absolutely, that's amazing. And it's great to find out again, what's good data versus what's bad data, and.
So they also take several plant species, but they corrected the data, so we can see little variation between the data.
Quick question: how did they how did they correct it? Can you go a little bit more into detail about the process of white carding?
I don't know very well the process, but I know that they take when they take this measurement, also they take the measurement of white surface. I don't know what kind of white surface. And then they normalize with that reading every measurement in here. I don't know really well how they did it, but it's a good question to if they can share more details about how they did the white card correction that they call it. With this data, we did the principal component analysis, and it was even better. This is what I can show you. Now, every ellipse is well apart from the others. This means that these signatures, this information is very particular to each species. So it's like a fingerprint signature. The light signature or the spectral signature is it's talking us about one species specifically. So that is great. We can see here how well the data or each species separates from the other one. And here is even the white card data. So when we did the classification method, we find an accuracy with this data set of 100%.
Oh,
This
yeah?
means that, yes, this means that we can use this spectral signature and predict with a 100% of probability that this is the coral, for example.
That's fantastic. That is just what great work. This is something that, again, goes to the fundamentals, of what we're trying to do, just what can you see? What do you want to measure? And, again, and of course the calibration as well. So if at a certain point, I definitely want to see what their method of white carding is, what material they use, all that fun stuff. We're using polystyrene foam generally as our substitute for Spectralon, because not everyone can afford Spectralon, and
No.
yeah, exactly. We have that cutting board. So like we had gotten like a silicon. I don't know why balloons flew up. We had our lead scientist, Dr. Petra Campbell. She was out in Alaska, and she had trouble keeping the polystyrene foam clean, so she was using a white cutting board. Okay, out there. So that's another one that we're looking at, and then we're also looking at because again, yeah, we're looking for accessibility and all that. We're looking at just white, pieces of paper, white construction paper, and then finally, to tie it all back in with Landsat as we should, white sand.
We will have to go to Quintana Roo as white sand.
It would be cool to have white sand, but it would be also cool to have like the other, just various different types of sand as well. But there's a whole like list of, places where Landsat calibrates against different sands. And it's a fantastic list. And so if there's any kind of sand that's, anywhere close to being to replicate it, that would be, just a great, learning tool and instrument, a fun way of doing this type of stuff.
Something similar. But
Go
we
ahead.
use it this time, beans, Phaseolus vulgaris. And what we did was to put two treatments, one without only soil and one with some chemical fertilizer. So the plants grow and we take the measurements in the plants. We have a lot of variation also, but this could be improved. And this could be improved, as you say, taking the measurement more near to the surface of the leaf. But we find some differences, very little difference between the fertilized treatments. What was the A without fertilizer and B with fertilizer. So the R readings were these ones, and then this one very similar, and the fertilizer readings were a little different from the other ones. So we can expect better improvements in the taking of the measurements, so we can discriminate between the fertilized plants, and the plants without fertilizer. That was what she did.
That's great. And then so those measurements were before correction. Is that what you were saying? Before
No,
they're
also we
after.
use the raw data. Yes.
Oh yeah, that's what. Yeah, okay. So you're using the raw data, so the irradiance data, and not the corrected. Okay, right on. That is, I mean, again, it's fantastic to know. It's that's really freaking useful.